Alright, in this video we'll be solving the 9709 February March paper 52 probability and statistics 1 paper. But before we get into the video, I just want to kindly ask that you subscribe to this channel. 81% of the people that watch these videos are not subscribed, and I know it may not mean like much to you, but to me it genuinely means a lot. And someday when this channel is much bigger, it's all going to be because of you guys. So thank you for your support in advance. Just as a disclaimer, I will not be displaying the actual questions for copyright reasons, so make sure you have a copy of the paper with you as we go through it. Number 1. Jacob throws 3 coins at the same time. The first coin is biased so that the probability of obtaining a head. Coin 1 is biased so that the probability of obtaining a head is 1 over 3. Go this head 1. And then second coin is biased so that the probability of getting a head is 1 over 4. And then the third coin is biased so that the probability of obtaining a head is 1 over 5. And we're given that the random variable x is number of heads obtained. Okay. So remember Jacob. I don't know why I find the name funny. Jacob throws 3 coins at the same time. This should probably be before the definition of x. So Jacob throws the 3 coins at the same time, and then we're told that the random variable x becomes the number of heads that Jacob obtains on the toss of those 3 coins. So part A says show that the probability that x is 2 is equal to 3 over 20. So probability that x is 2, that means that Jacob I'm sorry, I have no clue, but for some reason this name just sounds funny to me. Probability that x is 2, so this is we obtain 2 heads when the 3 coins are thrown at the same time. Okay, we should probably fill out the other info. So if the probability of getting a head is 1 over 3, it must mean that the probability of getting a tail is 2 over 3. And here probability of getting a tail would be 3 over 4. And probability of getting a tail here would be 4 out of 5. So we need to figure out all the possible combinations in which Jacob can get 2 heads. Okay. So we could either get head 1, head 2, and then tails 3. Because remember, Jacob is throwing the 3 coins, so only 2 of them have to show a heads, and then the third one by default has to show a tails. And then the other combination we could have would be head 1, tail 2, and head 3. Or the third one would be tail 1, head 2, head 3. Because in all 3 of these combinations we've got 2 heads, and so we can evaluate each one of those. So probability of head 1 and head 2 and head 3, head 1 is 1 over 3 times head 2 is 1 over 4 times tail 3, which is 4 over 5, plus head 1 is 1 over 3 times tail 2 is 3 over 4 times head 3 is 1 over 5 plus tail 1 is 2 over 3 times head 2, which is 1 over 4 times head 3, which is 1 over 5. And so let's evaluate each bracket. I've got 1 over 3 times 1 over 4 times 4 over 5 That's 1 over 15 plus the next bracket, 1 over 3 times 3 over 4 times 1 over 5. That's 1 over 20 plus 2 over 3 times 1 over 4 times 1 over 5. That's 1 over 30. And if we add these up, this does in fact give us 3 over 20. So therefore, the probability that x is 2 is equal to 3 over 20. Now, in questions where they ask you to show that this answer is correct, I urge you to show a lot of working. So here, instead of just punching this whole thing into the calculator, actually just go bracket by bracket and simplify step by step, because the purpose here is not to get to the correct answer, but to show step by step how we actually get to that correct answer. So make sure you show as much working as you can for show that questions. Part B, draw the probability distribution table for x. So x is the number of heads we can get when we throw 3 coins at the same time. So let's draw up our table. Our possible outcomes are we can get 0 heads from the 3 coins, or we can get 1 of the coins showing a head, or 2 of the coins showing a head, or all 3 of them showing a head. So we already know that 2 of them showing a head is 3 over 20. And then let's do probability that x is 0. So x is 0 means that none of them show a head. That's going to be probability of tail 1, tail 2, tail 3. So tail 1 is 2 over 3, tail 2 is 3 over 4, and then 4 over 5. 2 over 3 times 3 over 4 times 4 over 5, which gives us, this is 2 over 3 times 3 over 4 times 4 over 5, which is 2 over 5. I think I want everything over 20. We'll see if that works out. So I'm just going to multiply this by 4. So 2 times 4, that gives me 8. And then 5 times 4 is 20. And I'll do x is 3, because that will be easier than x is 1. And then we can just subtract. X is 3 means all 3 coins show a head. So head 1, head 2, head 3 is equal to, so head 1, head 2, head 3. So that's a third times a quarter times a fifth. A third times a quarter times a fifth. What does that give us? A third times a quarter times a fifth. That's 1 over 60. Okay. I thought we could have everything over 20. But no. Alright, so I'll just put everything over 60. You don't really have to do this, but I find that it's easier when all your probabilities have the same denominator. It's very easy for you to check if you've made a mistake or not. So I'm just going to multiply this by 3 in the numerator and by 3 in the denominator, so that it's 9 over 60. And I'll do the same here. 8 by 3, that's 24 over 60. Again, you don't have to do this. This is just preference. And so for x is 1, you could actually just keep in mind that if I add up all my probabilities here, they should sum up to 1. So if I want this last probability, I can just say 1 minus all these probabilities that I have should give me the probability that x is 1, instead of manually evaluating the probability that x is 1. Okay, so I think in that case, we'll do that because it is easier. Probability that x is 1 is going to be 1 minus 24 over 60 plus 9 over 60 plus 1 over 60. that's 26 over 60. And this here would be our probability distribution table. Or alternatively, for x is equal to 1, you could have said that x is 1 would be, you need one head from the 3 coins. So either h1, tail 1, tail 2, tail 3, plus tail 1, head 2, and then tail 3, plus probability of tail 1, tail 2, and head 3. And we're going to actually evaluate this just to double check that what we've done is correct. So head 1, we want head 1, tail 2, tail 3. So 1/3, 3/4, 4/5. 1/3, 3/4, 4/5 plus tail 1, which would have to be 2/3, head 2, that's a quarter, tail 3, that's 4/5, plus tail 1, that's 2/3, times tail 2, that's going to be 3/4, times head 3, which is 1/5. And so the probability that x is 1 here, we punch the whole thing into the calculator. That's 1/3 times 3/4 times 4/5 plus 2/3 times a quarter times 4/5 plus 2/3 times 3/4 times a fifth, and this gives us 13/30. And if you multiply the numerator by 2, denominator by 2, you get 26/60, which matches that. So yeah, in the exam, probably just go for the 1 minus approach. But if you want to be extra careful, then you can do both to double check that you're correct. Part C. Part C says, given that the expectation of x is 47/60, find var of x. Okay. So the variance formula as given by the MF19 is the sum of x squared p minus your expectation of x squared. Okay. So we first need to find this. The sum of x squared p means that I'm going to take my x value, square it, multiply by its probability, plus x value, square it, multiplied by its probability, and so on. So it's 0 squared times 24/60 plus 1 squared times its probability, which we have here, 26/60 plus 2 squared times its probability, which is 9/60. 9/60 plus 3 squared times its probability, which is 1/60. So if we punch this into the calculator, that's 1 squared times 26/60 plus 2 squared times 9/60 plus 3 squared times 1/60, and that gives us 71/60. And so we have that var of x is equal to 71/60 minus our expectation of x, 47/60, and this is squared. So if we punch this into the calculator, we have 71/60 minus 47/60, and this is squared. We get 2051/3600. Or if you want to give it as a decimal, this is 0.56 or 70 if you're going 3 significant. And that there is our final answer for number one, part C. Number two, last year an online store last year an online store sold a large number of computers. 55% of the computers were made by company If, okay, and 30% were made by G, and 15% were made by H. A random sample of 3 customers who each bought a computer from the store is chosen. So 3 customers chosen. All right. By the way, if you're wondering why all of a sudden it's daytime and in question 1 it was nighttime, it's because I didn't manage to finish recording this video last night because I had to go tutor. I've got students that I'm currently tutoring, so I had to go do that. And yeah, so I'm finishing this off the next day. And by the way, if you want help with A-level maths, you're struggling, and you want someone to assist you to help you to get your dream grades, then use the first link in the description down below, and I'll be very happy to assist you. Anyways, I digress. Part A. Find the probability that the 3 customers bought computers all made by different companies. Okay. So we can have 3 different scenarios here. So we've got customer 1, we've got customer 2, we've got customer 3. We could have customer 1 buying a computer made by F, customer 2 buying a computer made by G, customer 3 buying a computer made by H. But remember, this order can be swapped around. We could have customer 1 buying from G, 2 from F, and then 3 from H. Or we could have, oh, actually, this is long. This is 3 factorial. So we could have 6 different combinations. Because we could then do G, H, F. And I've missed another F, F, H, G. And I'm not doing this in the most logical way. H, G, F. Okay. These are the 1, 2, 3, 4, 5, 6 different possible combinations, because we're not told that customer 1 has to buy from F, customer 2 from G, customer 3 from H. They're just saying that they have to all purchase from different companies, right? So this can actually be done in 6 different ways. So if we find the probability of this arrangement, buying from F, that's a 55% chance, so 0.55, times buying from G, that's a 30% chance, 0.3, times buying from H, that's a 15% chance, so 0.15. And you find that this probability will be the same for this scenario, this scenario, this scenario, this scenario, and this scenario. Just that the numbers will be in different orders, but it will all multiply to the same thing. So instead of evaluating all 6 different scenarios separately, I can just multiply by 6. Or you could have said that I can arrange this FGH in 6 different ways, which would have been from 3 factorial. So instead of 6, you can put 3 factorial. Okay, I hope that makes sense. So we've got 0.55 times 0.3 times 0.15 times 3 factorial or 6, which gives us 0.1485. And that's our final answer. Part B, a random sample of 12 customers. Okay. So now we've got a random sample of 12 customers who each bought a computer from the store is chosen. Okay. And it says find the probability that fewer than 10 of these customers bought a computer made by company If. All right, so this is a binomial distribution. Reason being we now have a fixed sample size, which is 12. And then we have a probability of success, which is going to be the probability of buying a computer from company F, which is 55%. And our trials are going to be independent because one person buying a computer from company F is not going to influence the next customer that comes in to buy a computer. And then the last condition for a binomial distribution is that you need to have two outcomes, which are in this case either the customer buys a computer by company F or they do not buy a computer by company F. So this is a binomial distribution. But the telltale signs that you should look out are a random sample of n people is chosen and then have a fixed probability of success. If you have those two things, 99% of the time it's a binomial distribution. And the 1% of the time, wow, tough luck. I would define this as if as the random variable, we need to define what our success is. So we are counting the number of customers that buy a computer from company F. So buying a computer by company F is a success for us. Number of customers who buy a computer made by company F. And we know that F follows a binomial distribution with our sample size being 12. Probability of success is 55%. Write it as a decimal, 0.55. And we want to find the probability that fewer than 10 of these customers bought a computer made by company F. So probability that F is less than 10. Probability that the number of customers who buy a computer by F is less than 10. And so we're not going to evaluate F is less than 10 because that's long. We'd have to evaluate 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we would rather go the opposite direction. So we can do 1 minus the probability that F is greater than or equal to 10. And so now we just have to evaluate 10, 11, and 12 instead. So we can do 1 minus, we'll start with F is equal to 10. That's going to be 12, choose 10, times 0.55 to the 10, times our Q, or probability of failure, is 1 minus 0.55, which is 0.45. So 0.45 to the 2 plus 12, choose 11 times 0.55 to the 11 times 0.45 to the 1 plus 0.55 to the 12. So for F is 12, we're saying that all 12 customers buy a computer by company F. So it's just 0.55 to the power 12. Or you could just write it out using the formula. You'd still reach the same conclusion. Okay, let's punch this into the calculator. You get that the probability that F is less than 10 is equal to 0.958, correct to 3 significant figures. And then we are now given that a random sample of 140 customers who each bought a computer from this store is chosen. Okay, 140 customers chosen who bought a computer from the store. Use a suitable approximation to find the probability that more than 24 of these customers bought a computer made by company H. So we can define our random variable H. Number of customers who were interested in the customers who bought a computer made by company H. So this will be number of customers who bought a computer made by H. A computer made by company H. and H is going to follow the binomial distribution. Again, you can run through the four conditions of a binomial distribution, which are fixed number of trials, constant probability of success, trials are independent, and two outcomes. In this case, they're all satisfied because our number of trials is 140, which is fixed. Our probability of success, that's the probability of a computer by company H, which is the 15%. And then two outcomes, you either get a computer by H or you don't get a computer by H. And then trials are independent of each other because one customer buying a computer made by H is not going to influence the next customer's decision. Okay. So here our 140, but again, telltale signs, if you see a fixed number of trials, there's a good chance that it's a binomial distribution. 140 and then probability of success is 0.15. Now we're told to use a suitable approximation. At AS level, the only approximation you use is the normal approximation to the binomial distribution. But it is always good practice to check if the conditions for that are met. I don't know why I say that weirdly. But the conditions for that approximation are that NP should be greater than 5 and NQ should be greater than 5. So NP, just write out Q. Q is always 1 minus P. So 1 minus 0.15, which is 0.85. So NP in this case is 140 times 0.15, which is equal to 140 times 0.15, 21, which is indeed greater than 5. And Q becomes 140 times 0.85, which is equal to 119, and this is indeed greater than 5. So we can use a normal approximation since the conditions are met. Use normal approximation to your binomial distribution. You don't need to necessarily show this part, but it's just good practice to explain why you're using the approximation that you're using. You would only need to show this in a question that asks you justify the use of your approximation. This is exactly what you'd show, that these conditions are met. But when they just ask you to use a suitable approximation, then you don't really need to justify it. It's just good practice. Okay, so we know that if we can use a normal approximation, then H is going to follow a normal distribution with the parameters, the mean being NP, which is mean of a binomial distribution, the variance being NPQ, which is variance of a binomial distribution. So NP we already calculated to be 21. We need to find what NPQ is. NPQ would be 140 times our P, 0.15, times our Q, 0.85. So that gives us 17.85. So we know that H follows a normal distribution with mean 21 and variance 17.85. And now let's actually see what the question wants from us. Find the probability that more than 24 of these customers bought a computer by H. So probability that the number of customers who bought a computer by H is more than 24. But keep in mind that we are moving from a discrete distribution in the binomial distribution to a continuous distribution in the normal distribution. So we have to apply what we call continuity correction. And the way I like to think about continuity correction is that when we think of 24 as being a continuous number, it shouldn't be 24.5, that should be 23.5. When we think of 24 as being a continuous number, it's representing any number within this interval. So if I'm saying 24 in the context of a normal distribution, I mean any number from 23.5 to 24.5. If this was discrete, 24 means exactly 24. 23.5 is different from 24 if we're talking discrete conditions. But under continuous conditions, 24 represents any number from 23.5 to 24.5. So I need to factor that in. Okay. So with that in mind, we are saying we want h to be greater than 24. So if I was to draw some bars, and we'd have 24. We know 24 is bounded by 23.5 and 24.5. So 23 would be bounded by 22.5 and 23.5. 25, maybe let me drop that 24 down. And then 25 would be bounded by 24.5 and 25.5. And we are saying we want h to be greater than 24. So greater than 24 means we don't want to include any of the numbers within this interval because that's 24. So greater than 24, I'd start shading here, and I'd continue. If there were more bars on this side, I'd continue shading going to the right, because these are the values that I want that are greater than 24. So it means that I start off from 24.5 and we are going to the right. That's now our boundary. So we're saying h has to be greater than 24.5. So that's applying continuity correction. And if you're going the other direction, you just use the same logic. If you wanted h to be less than 24, I would have started from 23.5, moving this way, because I don't actually want to include the 24 when I'm going that way. So keep that in mind. So h is greater than 24, that's 24.5. That's our continuity correction. Now we need to standardize. So z is greater than 24.5 minus 21 over our standard deviation, so square root of your variance. So p z greater than 24.5 minus 21 over root 17.85, which gives us 0.828. And so if we sketch a mini bell curve, we've got 0.828 here. We want this region because greater than 0.828. So remember, our tables only read the area to the left. So from our table, we'll be able to get this area to the left. So what we can do is to say 1 minus the area to the left, because we know the total area under this curve is equal to 1. So if I subtract this unshaded region from 1, I remain with the shaded region. And so to write that, we can say 1 minus phi of 0.828. This means the area to the left of 0.828. And we go to our normal distribution tables. We read of phi of 0.828 to be 0.7961. And so this gives us a final answer of 0.2 or 4 to 3 significant figures. That is the normal approximation, 5 marks. And you know, the beauty of this normal approximation question is that it comes in virtually every paper, and it's always going to be the same procedure. You start off with some binomial distribution, and then you get its equivalent as a normal distribution, keeping in mind that your mean is the mean of a binomial distribution, variance is variance of a binomial distribution. Then you do your continuity correction, you standardize, and then you read your tables and get your answer for 5 marks. Okay. Number 3. The lengths of 250 leaves of a certain type of plant are measured correct to the nearest centimeter. The results are summarized in the table below. And we are given a table that has length in centimeters and frequencies. Just write F. Lengths in centimeters and their frequencies. So the first class is going from 5 to 9. Frequency 18. Second class is going from 10 to 14. frequency 28, third class 15 to 19, frequency 60, 20 to 24, 72, 25 to 29, 48, 30 to 39, 24. Okay. And then we are told part A. On the grid below, draw a cumulative frequency graph to illustrate this information. 4 marks. Okay, the first thing that you should do when you get either a question on histograms or cumulative frequency graphs, and you notice that your table has gaps between the classes. Because here in the first class, we're going from 5 to 9. In the second class, we're jumping, and then we're at 10 to 14. So if I drew vertical bars, we've got 5 to 9, and then all of a sudden, we've jumped 10 to 14. There's a gap here. So if it's to do with a sketch for a histogram or a cumulative frequency graph, your classes should not have gaps between them. If you find gaps, close them. And the process we use again is, in essence, just continuity correction like we did previously. But don't think about this one too much. We just need to close the gap between there. So you're going to subtract. You're basically moving both of these to the middle. So subtract 0.5 from 10, add 0.5 to 9, and then 9 is an upper bound, 10 is a lower bound. So what you do to this one group of bounds, you're going to do throughout. So for 9, I have to add 0.5. For 10, I have to subtract 0.5. So for every lower bound that I have to subtract 0.5. For every upper bound that I have to add 0.5 to close those gaps. So what that then does is that I'll just draw up a separate table. Let's copy this. Control C and V. And let's shrink that. Maybe not. So we want to, in fact, we want to subtract 0.5 from 4. So it becomes 4.5. We want to add 0.5 to 9. We want to subtract 0.5 from 10. So that now there's no gap here, right? It's airtight. So visually, we're now looking at something like this. We've got 9.5 there. And then the next one would be 14.5 there. And here we've got 4.5. And so here I add 0.5, subtract 0.5, add 0.5, subtract 0.5, and then add 0.5. Here we are going to subtract 0.5, 24.5, and then add 0.5, and the same thing for this last class. So 29.5 all the way up to 39.5. Okay. So these are now our adjusted classes with the gaps closed. Once we have this, we can move on to the next step. When you're drawing a cumulative frequency graph, on your vertical axis, you're going to have your cumulative frequency. And on your horizontal axis, you're going to have whatever your classes are. In this case, our classes are length in centimeters. Always put your units. We already have our length, right? But we don't have cumulative frequency, so we need to find what our cumulative frequency is. Oh my, we're going to draw up another table again. So I'll just copy and paste this below, because now we need to find our cumulative frequency. So I'll call that CF. And I'm just gonna erase this. So cumulative frequency is the sum of all the frequencies up and including that class, up to and including that class. The sum of all the frequencies up to and including that class. So for the first class, the cumulative frequency is 18. For the second class, it's 18 plus 28 because it's the sum up to and including. 18 plus 28, that's 30 plus 16, so 46. And then here it becomes this 46 because that's the sum of the first two classes plus the 60. So that's 106. And then here it becomes the 106, that's the sum of your first three classes plus the 72. So that's 178. And then here it becomes the 178 because that's the sum of the first four classes plus the 48. So that is, we put 2 there, 180 plus 46, so 226. And then if you add the 24, it should add up to 250 because we're told that we've got 250 leaves. So if we're looking at cumulative frequency of the last class, it should have all the frequencies added up together. Okay, so let's count the boxes and see if we can come up with a scale. So I've got one big box there, two big box, three big box. Oh man, these boxes are blinding. Four big box, five big box, six big box, seven big box. And here I've got one big box, two big box, three big box, four big box, and five big box. Okay, perfect. Now let's figure out what scale works. My cumulative frequency is going all the way up to 250, and I've got 1, 2, 3, 4, 5, 6, 7 big boxes. So how many times does 25 go into 250? Is that 10? So that's not gonna work. What about 50? 50 goes in 5 times. That could work. I'm trying to see if there's a better scale that we could use. But I think we'll just use 50 because everything else is not nice. Hold on, 20. Oh, 20 would be worse because 25 is 10. All right, we'll use 50. We'll do 50, 0, 50, 100, 150, 200, 250. For our lengths, they're going from 4.5 all the way to 39.5. 10, 20, 30, 40. That seems fine. So we'll use 10, 0, 10, 20, 30, 40, 50. Okay. Now let's plot. Remember, for a cumulative frequency graph, you plot your upper bounds against the cumulative frequency. Okay. However, do note that our lengths are actually starting from 4.5. So the first point that I have to plot is going to be 4.5 against a cumulative frequency of 0. Typically, you'd find that your classes start from 0. In that case, you plot 0 against 0. However, because here there's an exception, our classes are actually starting from 4.5. So it means that you have to start from 4.5 as well. So mark 4.5, 0. So 1, 2, 3, 4.5 would be here. So would mark that point as our first point. The next point is upper bound against cumulative frequency. So 9.5, 18. 9.5 is here. 18 here, we've got 50. So each box would be, what, 50 by 10, 5. 5, 10, 15, 18 would be somewhere there. I don't like the scale we used, but I couldn't find a better one. And then 14.5 against 46. 14.5. 11, 12, 13, 14.5, 46. So if I go all the way to 50, I subtract 5, I'm at 45. So 46 should be here. And then we've got 19,5,106. 19,5,106. 19,5 is here. 106. This is 105. So just over 105. 24,5,178. 24,5. So 1, 2, 3, 4. 24,5 would be here. And it was 24,5,178. Okay. Let's zoom out a little bit. 178. 150 is here. 55, 60, 65, 70, 75. So 178 will be somewhere in here. And 29,5,226. Okay. 29,5. So just there, and then 226. So that's 200, 205, 10, 15, 20. 5, 10, 15, 20, 25. So here. And the last one is at 39,5,250. 39,5 is here, and we want 250. So that would be here. Like that. And then you try to join your points with a beautiful S-shaped curve. Something like that. Okay. This becomes your cumulative frequency graph. Again, I hate the scale that we used. I don't know if there was a better scale given the grid, but yeah, that will be your cumulative frequency graph. Part B says 38% of these leaves failing to spell leaves at my big age, leaves are length k centimeters or more. All right. Use your graph to find an estimate for k. For questions like these, you'll find that it's easier to read less than on your cumulative frequency graph. So if 38% of leaves are k centimeters or more, it means that 100% minus 38%, which is 62, it means that 60% of leaves are k centimeters or less, right? And this value is much easier to read off from your cumulative frequency graph. So I would highly advise, if you get a question that says 38% of leaves are k centimeters or more, just invert the problem and look at it from the less perspective, because that's naturally how your cumulative frequency graph reads. Okay. So we can do 62% of our total number of leaves. We have a total of 250 leaves. So 62% of 250 is 155. And so you're going to go to your cumulative frequency graph, and you're going to draw construction lines from 155, and we want to find the corresponding length at a cumulative frequency of 155. So remember, each box is 5 units, so 155 would be there. Then draw construction lines. These are actually necessary, they're considered part of your working. Then we'll go down, 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 down. For me, it looks like it's 2122.5 centimeters. Again, read off the answer you get from your graph. Do not guess. They will mark you based on your graph. So if you get 23 on your graph, then use 23. If you get 21 on your graph, use 21. So in this case, I am getting that K has to be 20, we say 22.5 centimeters. So it means that 38% of leaves, right, this top portion, that's your 38% of leaves have length K centimeters or more. But we actually inverted the problem and we looked at it from the perspective of 62% have K centimeters or less. But it's the same thing, just different perspective, which is a life lesson. Sometimes it's easier to solve a problem when you look at it from a different lens. Part C. Calculate an estimate for the mean length of these 250 leaves. Okay, so for us to be able to get an estimate for the mean length of these 250 leaves, we're going to take each of our classes, and really it doesn't matter whether you used the adjusted classes or the original classes, because it's going to be the same regardless. We want to take our, I don't want to do that. Undo C. Okay. We want to take each class and we want to find the midpoint of each class. And the midpoint of each class will be representative of that class. So we'll use the midpoint of each class to help us then calculate the mean length. So the midpoint of 5 plus 9, that's 14 over 2, so 7. The midpoint of 10 to 14, that's 24 over 2, which is, oh, my math is atrocious. 24 over 2, 22, 1, 24, 2, okay. It's 12. 15 plus 19, okay, I'm not going to use my head anymore. 15 plus 19 divided by 217. That's shocking from me, 22, 27, and then 30 plus 39 over 2, 34.5. And so our frequencies are 18, 28, 60, 72, 48, 24. Okay. And now we want the mean. When you go to your MF19 and you're looking for the formula for mean, here we're dealing with grouped data that has been put into classes. That's what we call grouped data. So you look for the formulas under grouped data and you get the formula that says x bar is equal to the summation of xf over the summation of f, where in this case your x are going to be the midpoints and your f is going to be the frequencies. So to calculate this, you're going to take your x value, which is the 7, multiplied by its frequency, and do the same. 12 by 28 plus 17 by 60 plus 22 by 72 plus 27 by 48 plus 34.5 by 24, and divide this by the total frequency. So the total number of leaves that you have, which is 250. And then punch this into the calculator. So I've got 7 times 18 plus 12 times 28 plus 17 times 60 plus 22 times 72 plus 27 times 48 plus 34.5 times 24. Divide all of this by 250. We have 20.76, and that is an estimate for the mean length of our 250 leaves. Number 4, It has 16 toy cars. 8 are white, 5 are black, 3 are silver. It places all the cars in a bag and selects 3 of them at random without replacement. Part A. Find the probability that all 3 cars are the same color. Okay, so for him to get all 3 cars being the same color, it's either he picks white, 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 or, so we add, or he picks black, 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 or silver, silver, silver. And remember, this is all without replacement. So for the first white pick, we're picking out of 16 and we've got 8. But once we pick one car, we're only left with a total of 15 cars. And we want to pick another white car. We've already picked 1, so 7 must remain. Once we pick a second car, we're now looking at a total of 14 cars. And we've already picked 2 white cars, so it means only 5. It means only 6 white cars remain. So 6 there. And we'll do the same thing here for the black cars. So our first pick, we're picking out of 16. And we've got 5 black cars. Once we pick a car, we're only left with 15. We picked a black car on our first pick, so we only have 4 black cars remaining. And now we've picked 2 cars, so only 14 remain. And of those 14, only 3 will be black because 2 blacks were picked before. And now for the silver ones, we'll start with 16. We have 3 out of 16. Once we pick one car, we're left with 15. We picked a silver car, so only 2 are left. Now we've picked 2 cars, so only 14 cars remain, 1 of which is silver. And you punch this into your calculator. We get 67 over 560, or if you want to write this as a decimal, 0.12023 significant figures. Part B. Find the probability that when the 3 cars are selected, at least one white, and at least one black. Okay. So how can we achieve this? Let's write down all the possible scenarios that satisfy this condition of at least one white and at least one black. So if I want at least one white and at least one black, I could have WBW, W. So W, I think it's W. Okay. Funny thing is that I recently learned that the pronunciation, like W is literally double W, which is crazy. I've gone through 2 decades of my life without knowing that. But anyways, I digress. So WBW, that's a possible combination that satisfies at least one W and at least one B, right? Or we could have maybe WBB. Or we could have, are there any other combinations that we could have? Yes, we still have the silver cars, so don't forget those. We could have WBS. But I want you to keep in mind that in all these scenarios, right, there's different ways in which I can arrange these. So I also need to factor that in, because WBW can be written as BWW, or it can be written as WWB. This is still the condition in which we've got 2 whites and 1 black, right? Just arranged in different ways. So it means that once I evaluate this probability, I'm going to have to multiply that by 3 because I have 3 different scenarios. And the same will apply for WBB. Again, I could either have BWB or I could have BBW. So I'm going to have to multiply this by 3. For the last one, be careful, it's not 3 different. It's going to be 6 different. Because remember, you've got 3 different letters. You can arrange those in 3 factorial ways. Or you can just write down all 6 possible combinations. So let's do that. So for the probability, 3 times the probability of WBW. This is 3 times. We want to pick a white on our first pick. So that's going to be 8 out of 16. Once we've picked one car, we have 15 remaining. And out of those 15, I want to pick a black car, so 5. And now we've got 14 cars remaining. Out of those 14, I want to pick a white car. I've already picked a white car earlier, so I only have 7 white cars remaining. Okay. And what does this give us? That is 3 times 8 over 16 times 5 over 16 times 7 over 14, which is 15 over 64. All right, and then we want to do 3 times the probability of WBB, which is 3 times, we want to pick a white car on our first pick, so that's 8 over 16 times, we've picked one car, so only 15 remain, and out of those 15, we want to pick a black car, we've got 5 black cars, times 14, we want to pick another black car, so only 4 black cars remain. And so this is 3 multiplied by 8 over 16 by 5 over 15 by 4 over 14, which is 1 and 7. And then finally here we've got 6 times the probability of WBS. So that's 6 multiplied by, we want to pick a white car on our first pick, so 8 over 16, followed by a black car, so 5 out of 15, followed by a silver car, so we're picking from 14, and we have 3 silver cars, yeah, so that's 3 out of 14. And so this is 6 multiplied by 8 over 16, multiplied by 5 over 15, by 3 over 14, which is 3 over 14. And so these are all the scenarios in which we have at least one white car and at least one black car. So we can just tally those up. That's 15 over 64 plus 1 over 7 plus 3 over 14. That gives us 265 over 448 or 0.592. Okay, so I've just noticed that this year is supposed to be a quarter. I have no clue how I got what I got initially, but it's supposed to be 1 over 4. Okay, so let's add the stuff up. 1 over 4 plus 1 over 7 plus 3 over 14, 17 over 28. That's the probability of having or picking at least one white and at least one car in the selection of 3 cars. Number 5. The mass of peaches sold per day in a supermarket is normally distributed with mean 65.8 kgs and standard deviation 9.6 kgs. Okay, so mass of peaches normally distributed, mean 65.8 and standard deviation 9.6, so variance is 9.6 squared. Part A says find the probability that the mass of peaches sold on any given day is between 56 kgs and 75 kgs. Actually, I'm going to change this from a P because I don't want to be writing the probability of P. Okay. So it says find the probability, this part A, that our mass is between 56 and 75. Okay. So the first thing is to standardize. So standardize the 56. Remember your formula for standardization, x minus mu over sigma. So 56 minus our mu, which is 65.8, over sigma, which is 9.6, is less than. When you standardize the m, you get big Z, and then standardize the 75. So 75 minus 65.8 over 9.6. And let's simplify that. That's 56 minus 65.8 over 9.6. That gives us negative 1.021 to 3 decimal places. And if we do the same for the 75, we get 0.958. Okay. And you can sketch this out. We want the area between 0.958 and negative 1.021. This area here. That's what we're interested in. So, I mean, you can either memorize these formulas, right? Or you can, if you don't know the formulas, then you pretty much have to figure it out and derive it on the spot. But if you want the formulas, just go to my website. I'll link it down below in the description. It's the not the first link, it will be the second link. The first link is sign up for tutoring. The second link will lead you to the page where you can just go through all the formulas you need to know when you are dealing with the normal distribution, right? So here, the formula that you get will be phi of 0.958 minus 1 minus phi of 1.021. But the idea here is that we're just saying the area to the left of 0.958, which is your phi of 0.958, minus the area to the left of negative 1.021. There's this handy trick that says phi of negative z is equal to 1 minus phi of z. So with that in mind, then that just means phi of 0.958 minus this part here becomes that 1 minus phi of 1.021. If you ever get stuck in the exam and you're trying to figure out what to do, this is how you'd approach it. But hopefully you should be comfortable with just recalling the formulas, because that's much faster and will save you quite a bit of time. So go to your tables, read out phi of 0.958, you get 0.8309. I can't read my own handwriting. I'll just trust that that's 09. Minus 1 minus phi of 1.021, which is 0.8463. Okay. Let's punch that into the calculator and hope that it gives us the correct answer, which is 0.677. Perfect. That's part A. Now we are given that the mass of cherries sold per day in a supermarket is normally distributed with mean 72.4. So C. Excuse me. My body is fighting me today. It wants me to not do math, but the math must be done. C follows a normal distribution with our mass is 72.4 and standard deviation is sigma, so variance is sigma squared. It is known that on 10% of the days, less than 59.1 kgs of cherries are sold. Okay. So our random variable C here is representing mass of cherries sold per day, right? Cherries sold per day. We are told that the probability that the mass of cherries sold per day, which is C, is less than 59.1 kgs is equal to 10%. I hope that makes sense. The mass of cherries sold per day, that C, is less than 59.1 on 10% of the days. Okay. So we are going to use that to output so for sigma. So we are going to standardize. If you standardize your C, you get Z. By the way, this should probably come before the distribution. You have to define your variable first. I just defined it so that it actually makes sense how this probability part comes about. Anyways, standardize your 59.1, subtract mu, which is 72.4, over your sigma, and this is still equal to 0.10. So probability that Z is less than 59.1 minus 72.4, that is negative 13.3 over sigma is equal to 0.10. So now for readability, I'm just going to say let Z, small z, equal negative 13.3 over sigma. So I can actually write this as the probability that big Z is less than small z is equal to 0.10. And so if we sketch a picture of what's going on here, you will see that what we are looking at here, we're saying that the area to the left of Z is 0.1. The area to the left of Z is 0.1. So Z has to be somewhere here so that the area to the left of Z is 0.1. Okay. And the reason this is important is it tells us what sign we're going to put on our Z value. From this diagram, I can tell that Z is clearly less than 0 since it's on the left of 0. So whatever Z value I get from my tables, I'm going to have to make it negative because I can tell from my diagram that Z should be negative. Okay. Another problem we have is that our tables actually don't allow us to read probabilities that are less than 0.5. So we'll just do 1 minus 0.1, which is 0.9. The reason our tables start from 0.5 is because this 0.9 and this 0.1 are bound by the same Z value, right? The cutoff point there is the same. So it wouldn't be necessary for them to put table values for 0 0.1, 0 0.2, any number less than 0.5, because I can just find the Z value by doing the 1 minus of that number. So instead of looking for 0 0.1, I'll go to my tables and I'm doing argphi, which just means I'm reading my tables in reverse. So Z is equal to argphi of that. But keep in mind that we've already concluded from our diagram that Z has to be negative, so it has to be negative argphi of 0.9. So argphi of 0.9 means we're going to go to our tables and we're going to read them in reverse. So Z is equal to negative. If you do argphi of 0.9, you're going to get 1.282. Okay. So this means that, remember earlier we said Z is equal to that. This means that negative 1.282 has to be equal to negative 13.3 over sigma. And so sigma has to be negative 13.3 divided by negative 1.282. And so sigma therefore has to be 13.3 over 1.282, which is 10.4 to 3 significant figures, and that's our final answer. Now we are told that the supermarket is open 7 days a week. 7 days a week. So this should hint to a binomial distribution because we've got 7 trials, right? Our number of trials has now been fixed. Part C says find the probability that in a randomly chosen week, the first day on which less than. Okay, so now first day actually hints not to a binomial distribution, but to a geometric distribution. Find the probability that in a randomly chosen week, the first day on which less than 59.1 of cherries are sold is the fifth day of the week. Remember, a geometric distribution is just looking for that first success. And here we're looking for that first day with less than 59.1 kgs. So a success is a day that has less than 59.1 kgs. So I can define my random variable x here and say, let this be the number of days up until the first day on which less than 59.1 kgs of cherries are sold. So now this part here is just defining our success. So our success is the probability of getting a day with less than 59.1 cherries. So we can write that x follows a geometric distribution, and we were actually given this probability. If you go back to the stem of part B, where it says the mass of cherries sold per day in a supermarket is normally distributed with mean that and standard deviation that, it is known that on 10% of the days, less than 59.18.1 kgs of cherries are sold. So our probability of getting a day with less than 59.1 kgs is 0.1. That's our probability of success. And so coming back to our question here, they're saying find that the first day this happens is the fifth day. So the probability that x is equal to 5. We have our first success on the fifth day. And you go to your MF19, you get your formula for probability of a geometric distribution, and that's going to be q to the n minus 1 times p. So in this case, our q is 1 minus 0.1, which is 0.9 to the power of 5 minus 1, 4 times 0.1, 0.9 to the power of 4 times 0.1. That gives us 0.0656. And then we've got part D, which says find the probability that in a randomly chosen week, the first day on which less than 59.1 kgs of cherries are sold before the fifth day of the week. Okay, that's a mouthful. So they want us to find the probability that x, right, x being the first day on which less than 59.1 kgs of cherries are sold, is before, so less than the fifth day of the week, less than 5. Okay. So this is going to be, by the way, even though here we were told that the supermarket is open 7 days a week, the reason we concluded that this is a geometric distribution is because we're tracking the number of trials up until first success, which is literally the definition of a geometric distribution. So the 7, yes, it kind of hints to a binomial distribution, but remember, a binomial distribution would say that you're going to open the supermarket for 7 days, and then of those 7 days, we want to count our successes, which is not what we're doing. Here we're tracking up until first success. Part D, probability that x is less than 5. So here, Because this is discrete, when I say less than 5, I mean x is, remember we don't take x as 0 because you actually have to carry out at least one trial to get a success. So we start from x is 1, 2, 3, and 4 is the last number that we take, right? Less than 5, because this is discrete. So this is essentially the same as x is less than or equal to 4. And the reason why I wrote it like that is because I want to use this beautiful formula that says the probability that x is less than or equal to r is equal to 1 minus q to the r. If it was greater than, the formula you would have used is this. So these are two formulas you can use to save you the work. So if it's less than, you try to force it here. If it's greater or equal to, you force it here, and then you use the formula. So in our case, that's 1 minus q is 0.9 and r is 4. So probability that x is less than or equal to 4 is equal to 1 minus 0.9 to the 4, which is 0.34423 significant figures. Question number 6. Alisa has 10 different books from squares and circles, so 10 books. The books look similar, except I should probably write books in full because I want to use B for blue. The books look similar except for their color. Okay, oh, similar. There are 3 blue books, 2 red books, 2 yellow books, 1 orange book, 1 purple book, 1 green book. I don't want that to look like a 0, so I'll just write OR. 1 purple book, 1 green book. Okay. 3 plus 2, 5, 7, 8, 9, 10. Okay. That's fine. Alisa places the books in a row on her shelf. She is only interested in the arrangement of the colors. Okay. Part A, how many different arrangements? How many different color arrangements are there of the 10 books? So we've got blue, blue, blue. We've got R, R. We've got yellow, yellow. We've got an orange. We've got a, what's P? Purple. And a green book. And we've got 10 of them. So this is, you're arranging 10 items. So 10 factorial. Repetitions, we've got 3 blue books. So divide by 3 factorial. We've got 2 red books. Divide by 2 factorial. 2 yellow books. Divide by 2 factorial. And punch this into the calculator. You get 151,200. Part B. How many different color arrangements are there of the 10 books in which the 3 blue books are together, but the 2 yellow books are not next to each other? So they're saying of the arrangements in which the 3 blue books are together, how many of those do we have that the 2 yellow books are not next to each other? R, R, Y, 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 P, G. So we can go about this in a roundabout way, which is to say I can find the total number of arrangements in which the 3 blue books are together and then subtract the arrangements in which the 3 blue books are together and the yellows are together. And so if you think about it this way, let's say we've got this big box that represents all the total arrangements with absolutely zero restrictions, right? Which is the 151,200 from part A. Inside there, we're then going to have a subset where this represents that three blue books are together. These are all the arrangements in which the three blue books are together. Of those arrangements, we will find that some of them are going to have the Y's together, and some of them are going to have the Y's not together. So our interest is in finding the number of arrangements in which the blue books are together, but the Y's are not together. So it's this portion that we're interested in. And we can get that by saying, let's find the total number of arrangements in which the blue books are together, which is the whole red circle. And then let's subtract blue books together and Y's together, which is this unshaded part. Right. I hope that makes sense. So if we find the blue books together, that's just going to be BB. In fact, it's the display above this arrangement that we have above. That's just blue books together and no other restrictions. So that's 1, 2, 3, 4, 5, 6, 7, 8. So you're arranging 8 items, so 8 factorial. The R's appear twice, so divide by 2 factorial. Y's appear twice, so divide by 2 factorial. Minus, now we're saying that we want blue books together and Y's together. So that looks like this. You've got your blue books together, and you've also got your Y's together. And then you've got R, R, OPG. So now you're actually arranging 1, 2, 3, 4, 5, 6, 7 items. So 7 factorial, and the R's appear twice, so divide by 2 factorial. So if we do this, this is 8 factorial over 2 factorial times 2 factorial minus 7 factorial over 2 factorial. And this gives us a total of 7,560. And that is our final answer. Part C. How many different color arrangements are there of the 10 books with exactly 4 books between the 2 yellow books? Okay, let me see if I've got a yellow pen. Why do we not have a yellow pen? Okay. So we've got yellow and we've got yellow. And then we've got how many? 4, 1, 2, 3, 4 books between the 2 yellows. In total, we're supposed to have 10 books. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And really you can fill them out. But here, okay, let's fill them out. I think it will be clearer because we've got repetitions that we need to factor in. We have going to put OPG B. I've got another B and another B and 2 R's. So the way I want you to think about this is to say the blue letters can be shuffled around in these 1, 2, 3, 4, 5, 6, 7, 8 slots, right? Let's just assume for now that we've fixed the 2 yellow books in these exact spots. So let's say that our first yellow book is exactly in position 1, and then our second yellow book is exactly in, that would be 2, 4, 6, in position 6. Let's just assume that for now. We'll take into consideration later how we can move the yellow books about. But for now, we're assuming that they are fixed in these exact positions. So if they are fixed in these exact positions, the number of different arrangements we can have is just shuffling around these blue letters that we have, right? Which is those 8 letters. And that's 8 factorial divided by we're going to have our blue books. We've got 3 blue books, so we need to divide by 3 factorial. We've got 2 red books, so we need to divide by 2 factorial. These are the number of arrangements in which you've got the 2 yellows in position 1 and position 6, such that you've got 4 letters between them. Okay. But of course, this question did not tell us the exact positions of the yellow books. All they told us are that there should be 4 letters between them. So alternatively, we could have had a situation like this where I've got Y, Y, and then I've got one book before, 1, 2, 3, 4, and then how many? 1, 2, 3. Or we could even have had 2 books before, right? I could have 1, 2, 1, 2, 3, 4, and then 1, 2. This is a possibility. So now all that we need to do is to just figure out all the total different positions that the y's can take, because the calculation for this is exactly 8 factorial over 3 factorial times 2 factorial, because again, all you're just going to do here is find the number of different arrangements of the blue letters. And so if you just find the number of positions that the yellows can take up, and then just multiply this by that number, you are done. I do hope that makes sense. If it doesn't, let me know in the comments down below. So we can count the number of positions that our yellows can take up just by counting the number of positions that this last Y can take. So this is the first position it can take. It can take this position, can take that, 4, and then here it's gotten to the end. So we multiply by 5. So if you punch this into the calculator, this is 8 factorial over 3 factorial times 2 factorial times 5, which gives us 16,800. And now we are given that Alisa selects 4 books from her 10 different books from the series Squares and Circles. Part D, find the number of different selections if the 4 books include at least 1 red book, at most 1 blue book, and exactly 1 yellow book. Okay, so we've been told she's going to pick 4 books, right? 1, 2, 3, 4. And the restrictions are we need at least 1 red, at most, okay, 1 blue, and exactly 1 yellow. All right, forgot the T. Let's write down all the possible scenarios. So we could have 1 red, and I know we need to have 1 Y, and at most we must have 1 blue. So what are the other colors we had earlier? In fact, it doesn't really matter what the other color is. So I'll just use, what's a good letter? I was going to use O, but then I remember that we've got an orange book. So let's not use, I'll just use Z to represent other. Okay, so Z equals other book. So Z just represents any other book that's not specifically red, blue, or yellow. So 1 Z, okay, to make 4. And what are the other possible combinations we could have? We could also have 1 red and then 0 blues. We need 1 yellow. And this means that we must have 2 other books, which still adds up to 4. And then we need to have 1 yellow. I can also increase the red books to 2. And I can have 0 blue books and have 1 other book. I need to have 1 yellow book. I can have 2 red books. I can have 1 blue book and have 0 other books. I think those are all the possible combinations, and then we can evaluate each scenario separately. So one red book, remember we had two red books, so it's 2 choose 1 times one blue book. Remember we had, let me just write down we had 2 red, we had 3 blue books. How many yellow books do we have? We had 2 yellow books. And the other books would be, this is 3 plus 2, 5. It would be 3 other books, right? 1 orange, 1 purple, and 1 green. Okay. So blue, we want 1 blue from 3. So 3 choose 1. And then we want 1 other book from 3. So again, 3 choose 1. And then we want 1 yellow book from 2. So 2 choose 1. So that is 2 times 3 times 3 times 2, 36. And then here we're picking 1 from 2, and then 0 from 3, and then 2 from 3, and 1 from 2. So that's 2 times 1 times 3 times 2, which is 12. Now we want 2 from 2, 0 from 3, 1 from 3, and 1 from 2, which is 1 times 1 times 3 times 2, which is 6. We want 2 from 2, 1 from 3, 0 from 3, 1 from 2, which is 1 times 3 times 1 times 2, which is again 6. So the total is 36 plus 12 plus 6 times 2. So 12 plus 12, 24 plus 36, that is 60. Those are all the different selections. If the 4 books include at least 1 red book, at most 1 blue book, and exactly 1 yellow book. And that is also the paper as well. I hope you found that breakdown useful. If you did, please subscribe for more videos like this and comment down below which past paper would you like to see me break down next. Goodbye. I don't know if you guys can hear it, but basically there's an alarm going off in the background. We're just gonna have to wait for the people down there to sort that out and then we'll resume. In the meantime, how's your day going? How's life? Comment down below. What have you been up to these days? Apart from studying, of course, I know that school is a constant, so I mean, school is hard. But keep studying, stay in school, don't do drugs. But yeah, comment down below. How's your day today? An incident has been reported in the building. Please await further instructions. An incident has been reported in the building. Please await further instructions. An incident has been reported in the building. Please await further instructions. This thing is actually gonna make me mad. Ah, man.